Hello. Current limiters are very useful parts to drive LEDs with a defined current even with varying supply voltages, or to protect outputs against shortages, and for a lot of other applications. The function of a very simple current limiter and how to calculate all the necessary parts I will explain after the intro. Today I want to explain the function principle of a single transistor current limiter, the calculation of all necessary parts, and I will do some measurements on a real circuit. Here's a basic circuit of a single transistor current limiter. We need a constant voltage at the base of the transistor. We need a resistor in the emitter to measure the current, and of course we need a transistor to control the current into the collector. The voltage between base and emitter is 0.7 volt. So the voltage on the resistor is base voltage minus 0.7 volt. This voltage divided by the resistance of the resistor defines the current of the current limiter. Due to the high amplification of the transistor, we can neglect the base current to the emitter, and so the current in the emitter is more or less the collector current. If the current in the collector decreases, the emitter current also decreases, so the voltage drop on the resistor will also decrease. With a lower voltage on the resistor, but a fixed base voltage, the base emitter voltage will increase. This will open the transistor in such a way that the original 0.7 volts is reached again. If the collector current increases, e.g. caused by a shortage, the emitter current will also increase. This will lead to a higher voltage drop on the resistor. With a fixed base voltage and a higher voltage on the resistor, the base emitter voltage decreases. This will also decrease the current in the transistor, and this decrease will be in such a way that the originally 0.7 volt is reconstructed again. We can now summarize. This circuit stabilizes the voltage on this resistor. This causes a constant current through this resistor, and due to the effect that emitter and collector current are equal, the current into the collector is also stabilized. For current limiters with small transistors, we can use following assumptions. The base emitter voltage is about 0.7 volt. The minimum collector emitter voltage is about 0.4 volts in the normal operating range. And the voltage for the current sense resistor should be selected in a range of 0.5 to 1 volt. In our example, we will use later 1 volt. So with a base emitter voltage of 0.7 volt and 1 volt on the current sense resistor, we need a constant base voltage of 1.7 volt. And with a minimum collector emitter voltage of 0.4 volt and a current sense resistor voltage of 1 volt, we need at least from collector to ground 1.4 volt that the current control can work. For our example, we need the following data from the datasheet. Base emitter voltage 0.7 volt, minimum collector emitter voltage in the normal operating range 400 millivolt, amplification 200 to 450, and maximum power dissipation 500 milliwatt. Some further assumptions are that the voltage on the collector should vary from 1.4 to 37 volt, and the control voltage should be 5 volt. This makes it very useful to drive LED strings or use it as a shortage protected output at a Arduino Uno controller board. At first we define the desired current E. E should be 10 milliamps. Now we calculate the voltage on the current sense resistor R3. It is the minimal collector voltage minus the minimal collector emitter voltage. It's 1.4 volt minus 0.4 volt is 1 volt. The voltage at R2 is the base emitter voltage plus the voltage at R3. It's 0.7 volt plus 1 volt is 1.7 volt. The base current is the collector current divided by the amplification factor. To ensure that even the worst transistor with the lowest amplification gets enough current, we select the lowest amplification factor for our calculation. The base current is 10 milliamp divided by 200 is 0.05 milliamps. The emitter current is the sum of the base current and collector current. Due to the fact that the base current is very small, we can assume that the ER3 is roughly the same like the collector current. Now we have all information to calculate the resistance of the current sense resistor R3. R3 is the voltage R3 divided by the current R3. Is 1 volt divided by 10 milliamps is 100 ohm. Now we want to calculate the voltage divider R1 and R2. Due to the fact that we have a load current on the node, the calculation becomes difficult. But luckily, if we use a cross current which goes through R1 and R3, which is at least 10 times bigger than the load which is coming out of the node, we can use the formula of an unloaded voltage divider and have only a small error. We calculate our cross current 10 times E base, it's 10 times 0.05 milliamp is 0.5 milliamp. So we can calculate the resistance of R2. Resistance of R2 is voltage of R2 divided by cross current is 1.7 volt divided by 0.5 milliamp is 3.4 kilo ohm. Now we come to resistor R1. The voltage at resistor R1 is the control voltage minus the voltage at resistor R2. It's 5 volt minus 1.7 volt is 3.3 volt. The resistance of R1 is the voltage of R1 divided by the cross current. It's 3.3 volt divided by 0.5 milliamps is 6.6 kilo ohm. If we have these resistors in our collection, we can make serial and parallel connection of the resistors to get the 6.6 kilo ohm and the 3.4 kilo ohm. But this will lead to a lot of resistors. There's a better way to handle this. In the first step, we calculate the ratio of R1 divided by R2, which is roughly 2 to 1. We also know that the cross current should be at least 10 times bigger than E base. If we select resistors which are smaller than 6.6 or 3.4 kilo ohm, then the cross current is bigger than what we have calculated. So we select 2 kilo ohm for R1 and 1 kilo ohm for R2. Finally, we have to ensure that the maximum power at the transistor is not exceeding the maximum allowed power dissipation. First, we calculate the maximum collector emitter voltage. It is the maximum collector voltage minus the voltage at the current sense resistor R3. It is 37 volt minus 1 volt is 36 volt. Now we calculate the power in the transistor. It's the maximum collector emitter voltage multiplied with the current through the transistor. It's 36 volt multiplied with 10 milliamp is 360 milliwatt. The 360 milliwatt is less than the maximum allowed 500 milliwatt according datasheet, so at room temperature we should have no problems. At room temperature you can go up to 500 milliwatt maximum power dissipation if there is no further limitation in the datasheet without external cooling. If the maximum power is higher or the ambient temperature of the device is higher than room temperature, then special calculations are necessary to determine the proper cooling. How to do this I will show in another video. Here's the circuit where we will do our measurements. We have the transistor BC547B, here is the pinout. We have a current sense resistor of 100 ohm. We have a voltage divider with 2K and 1K. We will measure the current into the collector and we will measure the voltage at the collector. The control voltage is always 5 volt. In our first measurement we will increase the collector voltage from 0 to 2 volt and check whether the current limitation starts roughly about 1.4 volt. Here our measurement circuit. The two black lines go to the negative side of the two voltage sources. The red line is the voltage source for the collector current. The yellow line is the 5 volt voltage source. Here we have the 2 kilo ohm, 1 kilo ohm voltage divider go to ground. The middle point of the voltage divider goes to the base of the transistor. The emitter of the transistor go via the 100 ohm current measurement resistor to ground. The red line go to the current measurement device and this black line comes back from the current measurement device and goes to the collector of the transistor. Here we have the 5 volt for the voltage divider and here we can measure the voltage on the collector. I will now increase the voltage of the collector and we can see that roughly about 1.4 volt the current limitation starts and we end up in 9.35 milliamp. Now we will increase the collector voltage from 1.4 volt to 37 volt and check how stable our current is. We'll now quickly increase the voltage from 1.4 to 37 volt and we will look on the current what happens. And we see the current increases and increases. The reason for that is that the transistor gets hot and changes its behavior. I will do another video to look on this topic in detail and what we can do against it. The current stabilizes now roughly at 10.50 milliamps. I decrease now the voltage back to 1.4 volt and we look what happens again. Due to the cooling down of the transistor, the current decreases again. In our last measurement we will have a supply voltage of 12 volt and we'll put it first directly to the collector and then through one diode, through two diodes in series and so on up to 7 diodes in series. And we will measure the voltage at the collector and we will measure the current into this LED string. Here our last measurement. Our collector voltage on the red line is fixed at 12 volt. This red line goes to the amp meter and this black line comes back from the amp meter. This red line goes to the voltmeter. Each of the LEDs has a voltage drop of about 2 volts. When I connect the supply line via the amp meter directly to the collector, we will measure at the collector 12 volt. With each LED I connect in series, the voltage on the collector will decrease by 2 volts. Let us see. 12 volt, 9.5 milliamp. 10 volt, 9.5 milliamp. 8 volt, 9.5 milliamp. 6 volt, 9.5 milliamp. 4 volt, 9.4 milliamp. 2 volts, 9.4 milliamp. 0.5 volt, 4 milliamp. Now the voltage at the resistor is so low that we cannot any longer drive the 9 milliamp. And with 0.1 volt we can only drive a very small current through the circuit, now 60 microamp. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. Bye bye.